Okay, so now we're ready to look at the second half of chapter 10, which is gear trains. And gear trains are going to be when we have a series of mating gears, and they're going to be used to achieve larger speed reductions. So rather than just having one set of gears in engagement, now we're going to like connect them, and they're going to be related so that we can obtain larger reductions and keep it in a compact space. So for instance, if we want to go from 1800 RPMs to 10 RPMs, this would be a single velocity ratio of 180 to 1, which would mean if we would have one gear that was like, let's say 10 inches with a pitch diameter, we would have to have the gear that's engaged with it to obtain this velocity ratio 180 times larger, which would be like super big, right? So by breaking it down into smaller bits, we can actually create a train that is going to be more compact and more easily, designed into things. So so in this case, two gears, we would require that 180 times, but then we can kind of take it in steps as opposed to. So in this case, we might break it down into 3 or 4 reductions instead, but now it keeps it in a compact and a usable space type of an arrangement. So a train value is really going to be an overall velocity ratio when we multiply each of the individual gear pairs together with what their velocity ratios are. So if we look at equation 1035, it's a very simple equation, and this is going to be in our book on page 288. The equation for gear trains is just a TV, which is train value, is going to be equal to each of the individual velocity ratios multiplied together, okay? So velocity ratio number 1 times velocity ratio number 2 times velocity ratio number 3, and this really corresponds to the pairs as well. So if we look down at, now this is going to be an example problem we look at, but this gives us a nice picture of what a gear train can look like. So for instance, as we look at, this would be the top view and this would be the front view, okay? So if we have 2 gears that are in mesh, for instance, gear number 2 and gear number 3, if we go in orthographic projection up here, that is these 2 gears right here in mesh with one another. So this would be our input shaft on our first smallest input gear in engagement with a larger gear on the next shaft, which would be our output shaft. Now on that same shaft in front though, is going to be gear number 4, okay? So gear number 4 is going at the same RPM as gear number 3. These are connected on the same shaft, so they're rotating at the same speed. And now number 4 is engaged with number 5, which is over here, okay? And 5 is like in the background there. Now 5 is on the same shaft as number 6, which is a smaller one in the front here. And then these 2 are rotating at the same RPM. And now 6 is going to be an engagement with number 7, which is on the very last shaft over here. Okay, so you'll notice that we have one velocity ratio between these 2 that are engaged, a second velocity ratio, and a third velocity ratio. Now, if this would continue where there would be another, for instance, gear in front here and then engage with another one, we'd have an additional velocity ratio. So when we want to know what the train value is, the total velocity ratio from the beginning to the end, we simply multiply the individual velocity ratios, each pair together for however many pairs that there are, whether there's 2, 4, 8, 10, whatever they might be. Okay, so it's very, very simple math, quite honestly, very simple math. Okay. All right. So we are going to look at that example that we just took a peek at. And what we want to do is we want to determine what the rotational velocity is, W7, of that last gear, as gear number 2, the first gear, drives at 1800 RPMs counterclockwise. Okay. And we also want to determine what is the center distance between the shafts that are carrying gears 2 and 7. Okay, so let's go back underneath our camera. So we want to find out if gear number 2 is rotating at 18 RPMs counterclockwise, so W2 1800 RPMs. we want to know, what is W7 doing? What is W7 doing? Okay. So train value wise, we have to figure out what is the velocity ratio between 2 and 3? What is the velocity ratio between 4 and 5? And what is the velocity ratio between 6 and 7? And by knowing those, we can multiply each one of these together, and that's going to give us our train value. Okay. So we have to know information about these. So we already know the rotational speed of gear number 2. But then as we go to the next page at the very top here, it gives us more details about each one of these pairs. Okay. Now, so for instance, it says gear number 2, it has 12 teeth and it has a diametral pitch of 12. Okay. Gear number 3, we know that its pitch diameter is 2.5. So these two go together. Okay. Now, we know that if gear number 2 and gear number 3 are engaged with one another, their diametral pitches have to be the same, right? Okay. We also know that if we want to figure out center distances from gear number 2 all the way to gear number 7, then we really need to know the radiuses or the diameters of each one of these gears so we can figure that out. Okay. So how I would approach this problem, knowing that we have to know center distances, is you'll notice here for our first pair, they're giving us the pitch diameter of gear number 3. Gear number 3 with its pitch diameter, that helps us with center distance. So I'm going to find out what the pitch diameter is of gear number 2 then. Okay. And I'm going to do that very same thing for each of the other pairs that we have here. Find the pitch diameter for each one of them. Okay. If it's not given. So I'm going to get out a piece of paper here and we are going to do exactly that. Now it's been a little while since we looked at our equations that we have for gears. So not a bad idea to review. So for velocity ratio can be calculated using a couple different variations. It's towards the beginning. So I'm going to go over here. Here we go. On page 274, we have the options for calculating velocity ratio. So knowing the rotational speeds, but also the radiuses and the diameters. That's why I'm going to calculate the diameters each time, because we also need the center distances. So velocity ratio in this case is going to be the faster moving one, which is going to be D2 divided by D3. Okay. We already know what D3 is, so we have to find what D2 is. So to find D2, we know the number of teeth and the diametral pitch. So we do have an equation that relates those three. And that's way at the beginning. And it is on page 268. And here is our equation. Pitch diameter is equal to the number of teeth divided by the diametral pitch. So we can say that D2 is going to be equal to number of teeth divided by the diametral pitch of that gear. Okay. So we know that there are 12 teeth, gear number 2, and its diametral pitch is 12. But we know that diametral pitch never is given in with its units, but we know that it is teeth per inch. Okay. So teeth cancel out here. Inches are in the denominator of the denominator. So they're a multiplication of. So D2 is going to be equal to 1 inch. Okay. So now we can also calculate what the velocity ratio is by putting it up here. So our velocity ratio, and we'll call that velocity ratio number 1, is going to be equal to D2 divided by D3, which is 1 inch divided by 2.5 inches. Wait, I have that the wrong way, don't I? Let me go back and look. Yeah, I do. I think our D3 has to be on top, right? Yeah, our larger one has to be on top. So this is the faster moving is always the smaller number. So D3 over D2. I saw the D2.
Because we're looking between year 1 and year 2.
No, in this illustration,
Oh, that is.
it's gear 2 is the number 1. Yeah, I wish they would have kept it consistent because I glanced. I'm sorry. Number 2 is going to be our smaller, faster moving one that needs to go on the bottom. The larger gear needs to go on top. So I apologize. This needs to be 3 on top, 2 on the bottom. Please correct that. Sorry. So with that, let's do that again. 2.5 inches divided by 1 inch. Okay, so our velocity ratio number 1 is going to be, and we're going to put a negative in front. Just do it for me for a little bit. And when we do our calculation, it'll make a little bit more sense. 2.5, and that's it, just a ratio. So let's just kind of keep this on the side. This is our velocity ratio. And then we also want to kind of keep this on the side because we need to know what the pitch diameter is. And we also need to know that D3 is equal to 2.5 inches because we're going to use that for our center distance. So that's our first set figured out. We've got the velocity ratio and then the diameter for each one of the gears. So let's look at our second set. Our second set is gear 4 and gear 5. Okay, and we want to do that very same thing. Notice that we're given a diametral pitch here for gear number 5, which means that number 4 has to have the same diametral pitch, which is going to be 10 for each one. So here our velocity ratio number 2 is going to be D5 divided by D4. In the problem, we are given D5 as 3 inches. So we need to calculate D4 using the same diametral pitch and the 15 teeth. So D4 is going to be equal to the number of teeth on gear 4 divided by the diametral pitch. So we're going to have 15 teeth divided by 10 teeth per inch. Okay. So D4 is going to be 1.5 inches. So now we can plug that in here. So our velocity ratio number 2 is going to be equal to a negative 3 inches divided by 1.5 inches. So inches cancel out, and our velocity ratio number 2 is going to be equal to 2, right? So we'll put around there, and we'll say D5 is 3 inches. So we'll need that for our center distance calculation later and put a negative in front of there. Okay, so then our last set is gear 6 and 7. Okay, so go ahead and find the pitch diameter for gear number 7, knowing that it's 32 teeth with a diametral pitch of 8, and what the velocity ratio would be for that last set. D7, yep. So you should have a velocity ratio of negative 2.67 for that last one. Is that what you got? And then a pitch diameter of 4 for that's that gear number 7. Okay. All right. So then now I grab Another piece of paper. So now what we need to do is the question wants to know what is the W7 of that last gear. So what we're going to do is we're going to figure out the train value. And once we have the train value, then we can figure out how much slower, if you would, gear number 7 is going than gear number 2. So our train value, as we can see here, is going to be V1 times V2, VR1 times VR2 times VR3. So our train value is going to be VR1 times VR2 times VR3. So we're going to put our numbers in, and remember, we're going to put the negative in front, 2.5 for number 1, -2 for number 2, and -2.67 for number 3. Now, why are we putting the negative? The negative is in there for one reason only, and that is because when we go from gear number 2 to gear number 3, we switch direction. Okay. And then we do again from gear number 4 to gear number 5, we switch direction again, meaning rotational direction. And then lastly, we're going to do it one more time. So when we multiply the first two together, after we get to that second set, we're going in the same direction because we're going to have a positive number. But if we multiply a third one in, now we're back to a negative value. That means that from start to finish, we're going in an opposite direction. So let's kind of look at that over here. So between these two, we're going to have W2 is going to be going counterclockwise. So that means W3 is going to be going clockwise. Number 3 is going clockwise. So is 4 because they're on the same shaft, right? Then number 5 is going to come back counterclockwise. 6 will be counterclockwise. And then 7 will be clockwise. So now notice that their directions are opposite. We should end up with a negative value. Negative times negative is positive times negative. Sure enough, it is going to be a negative value. That is only to say that is going to be going in the opposite direction as that W2. Okay. So that means in our case, since W2 is going in a counterclockwise direction, W7 will be going clockwise. Okay. That's the only reason for the negative. Only reason. And it's kind of nice and it's convenient. And it's a good way to check. Okay. So I like it. So we're going to add that in there. But now we're simply going to take 2.5 times 2 times 2.67. And what do we get for our train value? Do we get negative 13.333 or negative 13 1/3? Is that right? Confirmed? I better check it. I just glanced at the book. Yeah. Okay. Perfect. So then that's our train value. All right. So that's the difference between, that means that number 1, W1, or I'm sorry, number 2, W2, our gear number 2 is going around 13.33 times, 13 1/3 times before number 7 is even going around once. Okay. Even going around once. So that's our speed reduction. So now we can say, all right, if we know our train value is equal to 13.333. So now that we're going to use it to calculate values, we don't need that negative anymore. The negative only is about direction. Okay. So we can also say that's equal to W2 divided by W7. We know that W2 is 1800 RPM. So to solve for W7, we would say W7 is equal to W2 divided by the 13.333, right? And then now we're going to have the 1800 RPMs divided by 13.333. And our W7 should be 135 RPMs. And we would say that it is going clockwise. So add the direction in there because of knowing that it's a negative value that comes out. Oh, thank you, Brandon. Negative 13.35. Good. A little bit of a rounding, I'm sure. Now that's part of the problem, right? So that's the first part. W7 is equal to 135 RPMs counterclockwise. Excellent. Now what we need to do is calculate what our center distance is. Okay. So now that we were thinking ahead, we calculated the pitch diameters for each one of these. So as we look here, we know the pitch diameter for number 2, but we only want half of that. So we want the radius of number 2, then the radius of number 3, the radius of number 4, of number 5, of number 6, and of number 7. Do you see that? Okay. So our center distance then for this train, our C, we'll call it 2 to 7. It's going to be equal to diameter of 2 divided by 2, diameter of 3 divided by 2, plus the diameter of 4, plus the diameter of 5, plus the diameter of 6, plus the diameter of 7, all of them divided by 2. Okay. So by doing so, we can fill in all our numbers. I'm not going to redo every one of these, right? It's a pretty simple calculation, but it should come out to be 6.75 inches. Okay. Between gear number 2 and gear number 7. That's the space, if you would, between the two centers. Any questions about that? So we went ahead and we calculated what the diameters were for each one if they weren't given with the information that we've got. We did the velocity ratios for each one, calculated the overall train value, used that to find out how fast W7 was going as W2 was going 1800 RPMs, determined that to be the 135 RPMs clockwise. And then our center distance was simply taking each one of those diameters, dividing them by 2 to get the center distance from that first gear to the last one. So pretty straightforward. Okay. Any questions on that? Okay. All right. Let's see what we got on our PowerPoint. What's next? Idler gears. Okay. An idler gear. So an idler gear is only used to change the direction of motion when we have a train, okay? Because of the fact that each time that we have two gears that are engaged with one another, they naturally switch directions, right? An idler is only used, it won't affect the train value. It is only used to change direction, but it will take up space. So it will affect the center distance, but it will not affect motion, okay? So let's look at figure 1022. On page 90, or on page 290. Underneath here. Okay. So here we've got gear 2 and gear number 4. Okay. As we look, we have a third gear in between here. So this is considered an idler gear. All right. So if we look at the velocity ratio between 2 and 3, and then the velocity ratio between 3 and 4. Okay, what we're going to find out is that if we look train value wise, and do we have, I don't know if we have numbers. Well, we can just put the variables in. So if we do our train value and we say the pitch diameter, oh, we do have diameters, but train value, tell them train value. Yep. It's going to be the velocity ratio number 1 times the velocity ratio number 2. And as we look here, the velocity ratio number 1 is going to be the diameter of 3 divided by the diameter of 2, okay, multiplied by the diameter of 4 divided by the diameter of 3, okay? So as we look here, if we multiply across the top, divide by the bottom, do you see how we can simply cancel out that D3? And the train value is not affected by that idler gear. 3 is the idler, okay? The only thing it does affect is that if we put the negative in front of each one of these, now the direction is going to be in the same direction as the input. Okay, that's the only thing that it changes. All right, and I should say the distance of the center distance from 2 to 4. Obviously, you have to add that in there. So if we know these numbers here, okay, for instance, we know that 3 is 6 inches. We know that 2 is 2 inches. Okay. Put our negative in the front. And then we know that D is 8 inches and 3 is 6 inches. Okay. These cancel out again. So really we're just going to take 8 divided by 2. Our overall train value is going to be a 4. Okay. And so we can, you know, if we take out 3, it would be a 4. We saw 3 cancel out here in both cases. Okay. So an idler gear is only there to change the direction. So if these two would be together, 4 would be going in the opposite direction of 2. But for some reason, it is advantageous to have 4 and 2 go in the same direction. So adding an idler gear in here will not change the dynamics of anything or the kinematics of anything. It's only going to change the direction to be in the same direction and also the center distance. Okay. So that's an idler gear. So let's look at problem number 1253. Okay, this one is going to be similar to your homework problem, but it's going to involve an idler gear. Okay, so as we look here, we need to determine the rotational speed of W8 as gear 2 rotates at 1200 RPMs counterclockwise. We also want to determine what the center distance is between gears 2 and 8. So I'm going to go underneath and we'll look at the problem itself. And the problem we're going to be looking at is number 53, and it's this set of gears right here. Okay, so we start with number 2 and we end with number 8. Okay, so as we look here, 2 is on a shaft by itself, but 3 and 4 are on the same shaft. 5 is by itself. 6 and 7 are on the same, and then 8 is by itself. Can you right away identify which one is the idler gear here?
5.
Number 5. Yeah, number 5 is our idler gear. Now, something to note about the idler gear. As we know, technically it's not going to change anything if we look at it in terms of the ratio, but it will change that direction. Okay, and we'll see that happen here, and it'll change the center distance. And what you want to do is, the last time when we did our center distance, we took all of those diameters and we divided them by 2. Okay, but we can't do that with our idler. We have to take the full diameter of the idler. Okay, because we would take one radius and then another radius where it engages, but it's actually going from one side to the other in engagement. So we take the full diameter of the idler, but then the radiuses of the other ones. Okay, so what I'm going to do is I'm going to let you get started on this one, and you're going to do it in the exact same way that we did our previous one. And the information for the separate gears is down here in the problem statement. Okay, so what you want to do is you want to find the ones that match up. So here we're going to have a velocity ratio number 1 between 2 and 3. Then we're going to have a velocity ratio number 1 between 2 and 3. Velocity ratio number 2 between 4 and 5. Velocity ratio number 3 between 5 and 6. Velocity ratio number 4 between 7 and 8. Okay. And remember, you're going to have to do center distance. So approaching it where you determine and make sure that you have pitch diameters for everything is going to make it a little bit easier when we need to do that part of it. So go ahead, and then it looks like there is a little bit of a typo. N7 should actually be D7, okay, because it's saying N7 is equal to 1.5 inches. That would be D7. So that's the pitch diameter number 7 is 1.5 inches. Okay, so go ahead and do that same process, starting out with finding the velocity ratio of the first set, finding the diameter when needed, second set, third set, fourth set, finding the train value, and then rotational speed. So I'll kind of do it alongside here. I can see here. So what I've done so far is I have the diameters and the velocity ratios. Is anybody have any questions on any one of these to this point? If you're kind of comparing with what I've got here. Okay. I just don't want to move ahead and I don't want to get too far ahead. The next step, if you're ready for it, is to calculate the train value using each one of these velocity ratios. Okay, so I'll leave mine here for another minute or so, and then I'm going to do that. So if you do need to compare, it's here still. Did you get the same thing as I did, DJ? Oh, which one did you do? Well, that's our homework problem. So, so BJ is working on the wrong problem, but that's okay. Process will be the same. And
So I was like, how is it so far?
yeah, 53 we want to be working on in class, but we use the same diagram for both.
Sorry.
That's okay. That's all right. All right, so I'm going to move to velocity rate, or I'm sorry, train value using the velocity ratios. So train value overall is going to be multiplying each one of the individual train values together. So the first train value was a -8. Second train value was 3.33. Negative as well, -1.1 for the third one, and -4.67 for the last one. So our overall train value, multiply it together. $36.85. That would be. And it would end up a positive value because we're taking negative times negative becomes positive, times negative is negative, times negative is positive again. Okay, so being positive means that from the start, W2 and W8 will be going in the same direction, okay? Or gears 2 and 8 will be going in the same direction. If we end up with a negative value, that means that they're going in opposite directions. So when we have the individual ones and there's only 2, they're going in opposite direction. All right. So any questions on train value? If not, no news is good news, I guess. We're going to then move to calculating our W7. So if we know that our train value is equal to W2 divided by I'm sorry, I said W7, W8. We have that extra gear in there. To solve for W8, we're just going to move it up to the top. Okay, so W8 is going to be equal to W2 divided by our train value. So W2 for this problem was 1,200 RPMs and was going counterclockwise, divided by 136.85, which is our train value from up top. So our W8 will be 8.769 RPMs. Okay. And because gear 2 is going counterclockwise, it's going to be going in the same direction. So W8 will be counterclockwise as well. All right, can I get a confirmation that I have somebody who has the same answer? I've been checking as I'm going along. Okay, good, Brandon. Thank you. Thank you. All right, so now that we have our W8 and we know its direction, now the last part of this problem. So this was one of the things that they were looking for. Now we need to find our center distance, okay? Now the reminder here is we have that idler in there. So now taking the radiuses of each one of these gears, but taking the diameter of number 5 or the radius twice, okay? Because we have to go across the whole thing and then get to number 8. So go ahead and calculate that center distance. This is going to be from 2 to 8. So we're going to have D2 divided by 2 plus D3 divided by 2 plus D4 divided by 2 plus D5. Okay, no divide by 2 plus D6 divided by 2 plus D7 and then plus D8 divided by 2. So then I've got to go back up. This one I don't have the final answer in front of me for. So I gotta, it's going to be 1 inch divided by 2 plus 8 inches divided by 2 plus 1.5 inches divided by 2 plus 5 inches plus 5.5 divided by 2. There we go. Okay, got that twice, so I'm pretty sure we're good on that number, and it looks familiar. So 17.75 for the final answer for the center distance. BJ, did you get that? If you're doing it with me.
No, I like said.
You're process wise, you're doing the other one, right? Yeah. Yeah, and the key to, no, don't be sorry. The key to this is really that idler, making sure you're getting the diameter there. Otherwise, the center distance will be off. Okay. Any questions on idlers? Is it possible to have 2 idlers? Yes. Yes, you could. The question would kind of be why. But you could, because you could switch it back another time. Because what you are, yeah, typically it will be 1 because your give up is going to be that center distance, right? Because neither one of the idlers will affect the velocity ratio. And unless you are truly trying to span a larger distance, then maybe, yeah. But yeah, typically it'll be 1. All right. So let's take a look at where we're at on our PowerPoints. We should be nearing the end. Okay. So this concludes, look at that. This concludes chapter 10. So you're ready now to complete all of the assigned problems in this chapter, including the ones that we had done before our break. And then let's look at the assignment to see which problems we are going to focus on and do. So I'm going to go backwards here. We're going to go to assignment number 5. Assignment number 5, and there are quite a few here, but the first couple are pretty straightforward. Remember, there is no CAD work to do here, and the last ones are going to be number 50 and 52 are going to be your train values, and then you've got some velocity ratios in here. So let's take a peek. I think we might have looked at these a little bit, but we'll kind of officially go over the homework here. So if we go back to page 295, I just want to be sure that I have 5, 6, 9, 13, 14. I'm just making sure before I go underneath here. 25, 26. Okay, got them. Okay. So on page 295 is where the problems start at the end of the chapter. So for numbers 5 and 6, we are only going to be doing part A here. Okay, so it's just center distance for these 2 problem descriptions. Okay, so each one of these is only worth 5 points because you're only doing the center distance equation. Now, center distance equation, you are going to find earlier in the chapter on page 268 here, page 268. Here are the center distance equations. Okay, there's one here using the physical distances or the pitch diameters divided by 2. And then you're going to notice that the other one is when we have numbers of teeth and diametral pitches. Okay. Then numbers 9, 13, and 14. Here we want to calculate the pitch diameter and the center distance for the description here. For each one of these, they have internal gears referenced. You want to only do external gears. Okay, we're just going to do external. So external gears for number 9, 13, and 14. Okay. Then number 15 and 16 is looking at the speed of the gear, which would be the angular velocity W, and the pitch line speed. That's going to be our VT for each one of these descriptions here. Okay. Angular velocity and pitch line speed equations are also in our chapter here. Just have to find just after this. Hold on. Okay. Oh, they were on that very same page. On page 274, here's your pitch line speed, and it relates back to the radius times the angular velocity of the gear that you're looking at. Remember, this has to be in radians per second, okay? And then your radius is going to be in whatever units you're working in, okay? So probably inches. So then it's going to be inches per second will be the final units for pitch line speed, okay? So that is that one. And that one, you're going to do the same two equations for 15 and 16. Then as we turn the page, number 25 and number 26, these two you're going to select gears for based on the descriptions. Okay, so it says we have a pair of 20-degree mild steel gears are to be selected for an application where they need to transfer 5 horsepower. The pinion drives at 1800 RPMs and the gear must rotate as close to 480 RPMs as possible. So it doesn't say you have to be exact, but you want to be close. Determine an appropriate set of catalog gears from table 10.7 for this application. Okay, so as you recall, I think it was example 10.10 that we did. And we used the tables on page 276, which is right here, continuing to 277. And each one of these groupings is diametral pitch, so that's the size of the tooth. And then these are the number of teeth inside of here that are commercially made, you know, on a regular basis. Okay. Now to pick your diametral pitch, what size tooth you're going to use, you're going to go back to page 275. And right here on this chart, this is going to be a suitable diametral pitch for 20-degree mild steel gears, which is what we're designing for. You're going to use the RPM on your pin, or I'm sorry, the horsepower and the RPM on your pinion, which is the faster moving gear. And you're going to find where that horsepower and close to your pinion RPM come together. And the number that you meet with is going to be where you start with your diametral pitch, which is then going to let you know which category you're going to be in here. So then those would be the gear, the number of teeth on the gear that you're going to be using to select for problems 25 and 26. Okay. And again, example number 10.10 that we went over in class in detail will be the process that you use for each one of these. And then finally, the last two problems you're going to do are going to be 50, doing the gear trains. So you're going to be determining what is the rotational speed of 5 as 2 rotates, whatever it says in that problem statement at the time, it ends at the top of the column here. And then for number 52, it's going to be just like what we just did on 53, but different numbers. Okay. And then this one has the idler gear in it. So that is your homework assignment then for chapter 10. Okay. Which includes, you know, kind of everything you need to know about spur gears. Okay. Are there any questions as you're kind of glancing here right now for those who are maybe online or in the classroom? Okay. If not, that's good. That's totally fine. I'll just kind of hang out here and be available to answer questions as they come up. But otherwise you should be, you know, working on any homework that we have in particular for this chapter 10, or on anything that you're maybe catching up on, you know, for getting handed in before the end of the semester. Okay. So the rest of the time is going to be independent. I don't have any other new information, so I will stop the recording here.